Google just made a move that sounds small on the surface, but could completely reshape the future of computing as we know it. They didn't launch one new chip, they launched two. Same generation, same company, same engineering team, but two completely different processors built for two completely different jobs. And that single decision is what's making people ask a serious question right now. Is this the beginning of the end for GPUs as we know them? Because to understand why this matters, you don't start with Google. You start with the basics, CPUs, GPUs, and what they were actually designed to do in the first place. Let's break it down from the ground up. The most familiar chip in the world is the CPU, the central processing unit. It's inside your laptop, your phone, your server, basically everything. And for over 50 years, it has been the brain of computing. A CPU is built around cores. Think of a core as a fully independent worker. Each one can fetch an instruction, decode it, execute it, and store the result completely on its own. So when a CPU has 8 cores, that means 8 separate workers sitting on the same chip. One might be running your browser, another your code editor, another your video call, all at the same time. But here's what makes CPUs powerful and also limited. Each core is extremely complex. It's not just doing simple math. It's predicting future instructions, rearranging tasks on the fly, caching data, and juggling thousands of operations per second using things like branch prediction and out-of-order execution. That's why CPUs are called general-purpose processors. They can run anything: games, operating systems, databases, AI, you name it. But that flexibility comes at a cost. Each core is big, expensive, power-hungry. And because of that, you can only fit a limited number of them on a chip. Most consumer CPUs have around 8 to 16 cores. Even high-end server CPUs might push past 100, but that's basically the ceiling. And for decades, that was enough. Until AI changed everything. Because AI workloads don't behave like normal software. At the core of modern neural networks is one simple operation, repeated over and over again at massive scale: matrix multiplication. You take numbers, multiply them, add them, repeat, that's it. No branching logic. No complex decision trees, just huge grids of math being processed again and again. A model like GPT or Gemini might perform trillions of these operations just to generate or process text. And suddenly, a CPU with 16 or even 100 cores isn't enough. Because even if each core is powerful, you're still doing a relatively small number of operations at a time. What you actually need is not a few smart cores, you need thousands of simpler ones. And that's where the GPU enters the story. Originally, GPUs weren't built for AI at all. They were built for video games. When you render a game, every pixel on the screen has to be calculated. A 4K display alone has over 8 million pixels, and most of those pixels can be computed independently. So GPU designers made a radical choice. Instead of a few complex cores like a CPU, they built thousands of smaller cores that could all work at the same time. A modern GPU, like NVIDIA's H100 class architecture, can have over 16,000 cores. But each core is much simpler. No heavy prediction systems. No complicated task scheduling. Just raw math performance. And all of those cores run in a special way called SIMD, single instruction, multiple data. That means one instruction gets applied across thousands of data points at once. Now here's where things get interesting. Around 2012, researchers realized something almost accidental. The math used in graphics rendering is extremely similar to the math used in neural networks. Both rely heavily on large-scale matrix operations. Suddenly, GPUs became the perfect accidental machine for AI. And that moment quietly changed everything. Companies like NVIDIA went from making gaming hardware to powering the entire AI. Today, nearly every major AI model is trained on GPUs. But here's the catch. Even though GPUs are incredibly good at parallel math, they were still designed as general-purpose parallel processors. They can do graphics, physics simulations, cryptography, AI, everything. Which means they are not perfectly optimized for any single one of those tasks. And that gap is exactly what Google decided to. Google started building its own chip around 2015. They called it the TPU, the Tensor Processing Unit. Unlike CPUs and GPUs, a TPU is not general purpose. It has one job only: accelerate matrix multiplication as efficiently as possible. Nothing else matters. No gaming, no operating systems, no flexibility, just raw AI computation. And the most important design choice inside a TPU is something called a systolic array. Picture a giant grid of tiny processing units. Each one is extremely simple. It takes two numbers, multiplies them, adds the result to a running total, and passes the result forward. Now imagine thousands of these units arranged in a structured grid. Data flows in from one side, waits from another, and the computation moves through the chip like a wave. Instead of constantly fetching data from memory, the data physically flows through the hardware. That's the key difference. Less time wasted moving data, more time doing math. The result is extreme efficiency. For AI workloads, TPUs often deliver far better performance per watt compared to GPUs or CPUs. But there's a trade-off. A TPU cannot do everything. It is not flexible, it is not general purpose, it is specialized to the point where it only makes sense for AI workloads. And Google has been using them for years already, quietly powering search, YouTube recommendations, Translate, and now Gemini. So you've already been interacting with TPUs without even knowing it. Which brings us back to Google's new announcement. They didn't just release a new TPU generation. They split it into two separate chips, two different designs, two different workloads, two different goals. One is built for training, the other is built for inference. And that difference is extremely important. Training is what happens when you build the model. You feed it massive data sets, run trillions of calculations, and update weights across billions or even trillions of parameters. It is compute heavy. It is massive. It requires thousands of chips working together in huge clusters, constantly communicating gradients and synchronizing updates. That's why Google's training system is built at absurd scale. They connect around 9,600 TPU chips together into a single pod. And they claim it delivers around 121 exaflops of compute, scaling up to 1 million chips in a single logical cluster. Training is about brute force scale, but inference is different. Inference is what happens when you actually use the model. You type a question, and the AI responds. Instead of huge batches of data, it processes one token at a time, and every step depends on the previous one. That makes it memory sensitive, not just compute heavy. And it gets even more complex with long conversations. The model has to store something called a key value cache in memory, which grows with every token it generates. So now, instead of just doing math, the system is constantly waiting on memory access. And when you move into AI agents, the workload gets even heavier. An agent doesn't just answer once it loops, reasons, calls tools, plans, and retries, sometimes going through thousands of micro-steps in a single task. Every small delay adds up, which changes everything about how hardware must be designed. That's why Google separated training and inference into two different chips. One built for massive training clusters, and the other for fast, low-latency responses. The inference chip also uses about 384 MB of ultra-fast on-chip RAM, reducing memory delays, while both chips run on Google's Axion ARM CPUs, giving full end-to-end control and up to 2x better performance per watt. Zooming out, the industry implications are becoming serious. NVIDIA has long followed a simple strategy: one GPU architecture, one ecosystem, capable of handling everything from training to inference and simulation. The idea was to scale hardware and let software adapt. But Google is challenging that directly, arguing that workloads have diverged too much for one chip to handle efficiently. Even though NVIDIA's stock only briefly dipped and quickly recovered, the real signal wasn't price, it was direction. Google is essentially pushing a shift towards specialized chips for different AI stages, hinting that the future may move away from general-purpose computing toward highly specialized hardware. If you want a deeper breakdown of how these chips actually handle AI workloads step by step, make sure to leave a comment. And don't forget to like the video and subscribe for more deep dives like this, because the next wave of computing is already being built, and most people haven't even noticed yet. Thanks for watching. See you in the next one.